Okay, hello again. Topic 1, stoichiometry, particle nature of matter and chemical change. These are some of the things that you'll hopefully be able to do by the end of it. Very important skill will be balancing and writing chemical formulae. Very important thing to pick up from this session. But to begin with, overview of particle theory. So all matter is made up of particles. These particles are moving around, so they have this kinetic energy above 0 degrees Kelvin. So this is a theoretical value that we've got close to, but very, very cold, -273.15 degrees Celsius. And as we come away from that, particles get more and more kinetic energy, and the amount of that energy is proportional to the absolute temperature. So this absolute temperature means temperature in Kelvin. So here, as you can see underneath, we've got solids, liquids, gases. Probably familiar with a lot of the terms involving moving between them. Melt it, give it some energy, get to the liquid. You see the particles are now rolling over each other, a bit more energy, vaporizing it. We've got these free moving gas particles much further apart, occupying the volume of their container. Coming back the other way, cool things down, condense them, we're going to end up with a liquid, and then we can freeze them back to our regular array of a solid. Two maybe new terms: sublimation. Things that will sublime would be iodine. Maybe you see that in the lab, heating some solid iodine, that will form a vapor very readily without going through a liquid state. And then deposition. If you think of frost forming on the ground in the winter, that's an example of water vapor becoming ice particles very quickly. Snow is another example of deposition as well. So phase changes, we talked about moving through these phase changes as we increase the temperature. Interesting thing on here perhaps is that as we go through a phase change, we don't see the temperature changing. So during these sections, temperature's changing, we're dealing with kinetic energy changes. During these sections, we're talking about potential energy. And you might like to think of your fridge at home. If you think of your fridge, you've got various stages going on. If we think of inside the fridge, we've got to get the heat out of it somehow, and we have an evaporation process going on. So we're going from liquid to gas, and you can see it's going to be taking in energy during this phase to form the gas, and that energy comes from the air that's in there, so the fridge itself gets colder. Some definitions here that you can look at in your own time: elements, mixtures and compounds. Have a read of that. Right, writing formulae. Now this is really important chemistry now. Sometimes we're going to have a clue, and you're going to see some of these prefixes. So carbon monoxide, mono, 1, disulfide here, 2 of them, triceratops, vanadium trichloride, you've got 3 Cls, tetrachloride, 4, pentagon, phosphorus pentabromide, hexagon, you've got 6 sides of the hexagon, sulfur hexafluoride is SF6. Now, what I'm going to show you is a little system you can use to write formulae. It involves something called combining powers. Now, as we do more on electron loss, electron gain and covalent bonding and things like that, we'll understand where these formulae are coming from. But for now, if you want to be able to write formulae, this is one way that you can go about it. So I've got my periodic table here, 8 groups, and I've numbered them 1, 2, 3, 4, 3, 2, 1, 0. And there are 3 types of compounds that I'm going to need to be able to name. Simple binary compounds, binary 2, where there's just 2 elements in it. Transition metal compounds, where we might see these Roman numerals coming into play. And compound ions. And this table here contains all the important compound ions, plus hydrogen carbonate, which I seem to have missed off there. But all the important compound ions that you'll need for writing formulae. So let's look at some examples, starting with these binary compounds. So the way it works is we look at the elements, look at their position on the periodic table, and look at their combining power. So if we take sodium chloride, this is what we're working with. Sodium's in here, chlorine's in here, each have a combining power 1. We cross over those numbers and we end up with that formula. Silicon dioxide, well, silicon is here in group 4, oxygen's here underneath the 2 column, and so we write them underneath, cross them over, and then if we can cancel, if there's a common factor, we cancel them down and we end up with SiO2. So those are the binary ones. You're going to get to practice a lot more of these in class. If we've got Roman numerals, then instead of having to head over here to look for a combining power, we can very simply just use the Roman numeral as it stands. So copper 1 chloride means that my combining power is 1. Copper 2 chloride means the combining power is 2. Final 2 examples here are these compound ions, carbonate, sulfate. Again, if I look back to here, I can just look these up in the table, carbonate, sulfate. Again, note down the combining powers, cross them over, cancel if necessary, and write down the formula. Noticing in this example here, I need 3 lots of sulfate, so I'm using brackets to show I've got 3 lots of the whole thing. Right, next thing, balancing equations. So once we've been able to write these formulae, we need to be able to balance chemical equations, and really this comes down to a little bit of experience but also a lot of practice. So you write down the formulae as they stand. So this example here, iron with oxygen giving us iron oxide. I would have had to deduce this, work it out from my combining powers. Then I need to start putting numbers in front. That's where I'm allowed to put them. These coefficients, I can write numbers in front until I get the same number of each type of atom on both sides of the equation. One thing to be careful of, that catches out even the most experienced of chemists, is that they forget that some elements in their natural states are diatomic. So if a reaction involves oxygen, it's found as O2. Once it's combined, reacting with something else, you can forget about this. But if you find in your equation one of the starting materials or products, indeed oxygen or hydrogen or nitrogen, remember that these are diatomics. And then you can also, at the end of that, you can add in some state symbols. So if something's a solid, at the conditions that you're working, S. If something is a liquid, L. If something's a gas, like the oxygen here, it's a G. If something's dissolved in water, it's AQ, which stands for aqueous solution. So here are 3 examples. Maybe you can have a go at these. Pause me for a second and I will write the answers underneath. So we've got potassium being added to some water to produce potassium hydroxide, which if I didn't know the formula I'd need to work out from my combining powers, and hydrogen. Hydrogen was one of the ones we saw that was diatomic. So balancing that, I'm going to have to do 2 of those, 2 of those, 2 of those, and then I can also put in state symbols if I wish. Solid, liquid, this is going to be a solution, and that's going to be a gas. Next one, sodium hydroxide, which is a solution, reacting with hydrochloric acid, which is a solution, to produce sodium chloride, which is a solution, and water, which is a pure liquid. And that, looking at it, is already balanced as it is. The last one, methane, coming out the gas taps, reacting with air. Well, it's reacting with the oxygen in the air to produce carbon dioxide and again water vapor. You think of what goes on in the laboratory. Balancing this, I should probably put 2 there to get the H's sorted out. 2, 2, and then 2 there like that. Okay, so it's all about practice, but what you've seen today in terms of writing formulae, balancing equations, is hugely important to being able to do the rest of this chemistry course. So this is what you should have picked up. Hopefully it's made sense to you.